In this lesson, we're going to focus our attention on understanding appropriate metrics that can be used, as well as various scheduling algorithms and evaluation of those algorithms related to non-preemptive scheduling as well as preemptive scheduling. And so first, let's focus our attention on how do we evaluate an appropriate scheduling algorithm. We can do this by taking into consideration appropriate metrics of interest. And these metrics of interest relate to understanding appropriate throughput, average turnaround time, average wait time, and average as well as response time. And so when we think about throughput, we're looking to quantify the number of jobs that are executed during in a specific time interval. And when we think about the average turnaround time, we're trying to quantify the time that it takes for a job to complete. When we discuss the wait time, we are looking to quantify the average time that a job experiences in waiting to be processed. And response time relates to the turnaround time for a specific job that we have. And so when we think about this, we can quantify those with specific measurements um, to evaluate or quantify these values. What we want to keep in mind is that we consider metrics such as throughput and average turnaround time and average wait time to be system-centric metrics, while response time is going to be what we consider to be a user-centered metric. And so with this in mind, this is a high-level table that kind of conveys the overall metrics of interest when we're evaluating scheduling algorithms and their performance. And when we think about appropriate metrics for starvation and convoy effect, you want to keep in mind starvation is going to signify denial of service, and it's intrinsic due to intrinsic properties of the schedule. The convoy effect is going to evade is going to relate to detrimental effects due to appropriate intrinsic properties of the scheduler. And these are both qualitative metrics that can be utilized. And so when we think about the various metrics that we discussed, let's consider that we want to think of the most user-centric metric of a scheduler. And what is considered a user-centric metric? Is it throughput? Is it the average waiting time, the average turnaround time, CPU utilization, response time, or none of the above? And if we want to think about this, we can simply refer back to our table. And in the table we have in the discussion with this, we see that response time and variance response time are the metrics that are user-centric. And so for this question, we can denote that response time is going to be an appropriate metric that is user-centered. And so let's further discuss some considerations as it relates to scheduling algorithms. And we've discussed the idea of non-preemptive scheduling algorithms. And in this regard, what we think about is that is a non-preemptive algorithm is basically denotes that the scheduler doesn't have control over uh, the processes as they're executing once they've been scheduled on the CPU. And so the scheduler can um, only take control once the process itself decides that it no longer needs the CPU and needs to terminate execution. And typically that can be done by making an appropriate blocking system call, like a IO request. And so we can discuss some of the various scheduling, non-preemptive scheduling algorithms. We have the first come, first served algorithm, and we have the shortest job first algorithm. These are both considered to be intrinsic. And then we also have priority, which is considered to be an extrinsic. And so when you are evaluating or utilizing the scheduling algorithms, you want to keep into mind appropriate resource requirements related to each process. And so here we want to consider both the CPU and IO burst times for each of these processes. And so for P1, we see it has a CPU burst time of 10 and IO of 10. P2, CPU burst time of 1 and IO burst time of 2. And for P3, we see a CPU burst time of 2 and a IO burst time of 3. And you want to keep into mind that the CPU burst is going to be representative of the continuous CPU activity by a process before it requires an IO operation, while the IO burst time relates to the activity initiated by the CPU on an IO device. And so with this in mind, we want to take into consideration the arrival order of these processes. And in this case, we have P1, P2, and P3 arriving in order at nearly the same time. And we want to also consider that each process uses CPU bursts, IO bursts, and CPU bursts, and then they are done. And so let's first take into consideration first come, first serve uh, non-preemptive scheduling algorithm. In this case, we want to consider the arrival time of the process to be representative of the intrinsic property. And so the arrival time is going to be based upon the time when the application launches. So if we launch an application like iTunes at time t0, and then we also launch QuickTime Player at time t1, then iTunes has arrived earlier than the QuickTime application, and therefore um, the scheduler takes that into consideration. So during the execution of these two applications, the programs, whenever each program is ready to run, uh, iTunes will get picked first since it had an earlier arrival time. And so the priority in this case for iTunes is over the priority for the QuickTime Player application. And so let's consider how we could evaluate this with regards to appropriate times that need to be taken into consideration. And we want to discern what are the wait times that we need to take into consideration. And So we consider that we have a CPU, IO, CPU, and then the processor behavior is completed. So with this, in this consideration, we have the CPU and IO times, and we want to evaluate this by highlighting each of these process times. So we have P1 of 10, 10, and then P1 of 10 again. And so when we want to evaluate uh, both the waiting time based off of the response time minus the minus the that execution. And so here we can determine that T1 has a total time of 30, T2 is 31, and T3 is 33. And so what is the value that we have for this time? So taking this into consideration, we can have that the time to be 10 plus 10 plus 10, so that we have calculated for that time frame. And then we know that T1 has a time of 30 based off of the CPU time that we've calculated here. And so the wait time for P1 is going to be 0. And so we can do the same calculations for P2 as well as P3. And so in this case, we have for process 2, the wait time is going to be 31 minus 4, which is going to equal 27, because we have that the time for the CPU is going to be 31. And then we calculate 1 plus 2 plus 1 to be 4. So 31 minus 4 is going to be equal to 27. And then we can do the same as well for process 3 also. So we're going to have 33 minus 7 equals 26. And so you want to keep into consideration what might be some appropriate considerations for utilizing the first come first serve algorithms, and that could result in high average waiting times. And so in this case we have 53 of 3, and then we also have high average turnaround times, and in this case it's going to be 94 out of 3. And so in regards to the convoy effect, we see this with regards to P1 as illustrated. And you want to remember that when we're talking about the convoy effect, we're trying to qualify uh, what affects, what intrinsic properties are detrimental to the execution of the process on the scheduler. And so we can also take into consideration the shortest job first algorithm. And so in this case, we keep into consideration the times for each process. And we have our arrival order, P1, P2, and P3, as well as the CPU bursts, IO bursts, and CPU bursts, and then they are done. And when we consider the shortest job first, this means that we're making a decision to execute the job based on the intended um, execution time. And so we want to have a knowledge of the CPU burst time for each process. And once we um, know the activities and the times for the CPU and IO bursts, we can use the shortest job first scheduler to provide for a mechanism in which we're going to execute the shortest CPU burst process first. And so if we take this into consideration using the previous approach, we want to identify what processes are ready. And with this in place, we see that P2 has a CPU burst of 1. And so that is what is going to get executed first. And so P1 and P3 are then both considered to be ready. Comparing the two, we see P3 has a value of 2, P1 has a value of 10. And so in this case, P3 is going to be picked. And so now with P1 being the only process remaining, it is now ready to execute. And so if we wanted to calculate the appropriate waiting times, we can do that as well. For T2, we have a value of 4, P3, a value of 16, and T1, a value of 34. And so when we consider execution and the wait times for each, we can calculate T1 minus E1. And so we have 34 minus 30 for P1, 4 minus 4 for P2, and 16 minus 7 for P3. And so we want to consider appropriate considerations that can be made when we want to evaluate potential qualitative metrics. And so we can denote that we have a potential for starvation, which might mean that we might have denial of service for this process due to basic intrinsic properties of the scheduler. And so we want to consider that we have a low average waiting time using the shortest job first, 14 out of 3, compared to first come, first serve, which had a 53 out of 3. And we also have a lower average turnaround time as well, which will equate to 54 out of 3. And for first come, first serve, it was a value of 94 out of 3. And so when we compare the processes for shortest job first and first come, first serve, we can see that the shortest job first underutilizes the CPU in comparison to the first come, first serve scheduler. And so now we can also take into consideration appropriate guidelines that we want to consider when we are evaluating extrinsic schedulers. And so we also want to keep into consideration when we think about extrinsic properties. We're talking about the priority and trying to relegate how each process is important compared to the other processes with regards to scheduling and execution. And this can be illustrated in most operating systems that uh, specific tasks are going to be given a default priority that can either relegate them to being more important or better served for execution over other processes. And so with preemptive scheduling, we want to consider that we can yank a processor from a currently running process at an opportune moment, and that will allow for it to have a higher priority in the process. And so some things that we need to consider is what denotes as an opportune moment, and how can we determine what is going to equate to a higher priority. And so let's consider the algorithms that we've discussed, first come, first serve, uh, shortest job first, and priority, and considering those with preemption, and also discussing round robin. And so when we consider first come, first serve, we're talking about opportune moment is going to be when a process rejoins the ready queue after IO completion. And so first come, first serve without preemption, we have the utilization of the IO and CPU. And so in this case, with preemption, we deschedule P2 and we schedule P1 because it has a earlier arrival time when compared to P1. And so in this case, without preemption, we have P1 complete at a later time for both CPU and IO than with preemption. And so how can we accomplish shortest job first with preemption? In this case, it results in shortest remaining time first. And so when we think about what might represent an opportune moment, this could be when a process rejoins the ready queue after IO completion, and then we want to estimate the remaining time to make the preemption decision. And so in this case with P1, we compare it to P2 and P3. So we have a value of 10 for P1, and P2 has a value of 20. P3 has a value of 25. And so in this case, P1 is ready. P1 has a value of 7, P2 has a value of 10, and P3 has a value of 25. So we deschedule P2 and we'll schedule P1 because it has the shortest time remaining. So at this point, P1 is complete. And in this case, we have P2 and P3 available on the ready queue. We can add P1. P2 now has a time of 6, P1 of 7, and P3 of 25. And so this will result in us continuing with P2. And so how can we do priority with preemption? In this regards, we reevaluate priority on IO completion. So in our ready queue, we have P2 and P3, and we also have P1 now added with P2 and P5. So in this case, initially we had P2 ready for scheduling. We will deschedule P2, and now we will schedule P1 as it has the highest priority. And so another consideration for preemptive schedulers is round robin. And so with a round robin scheduler, we consider an opportune moment is when a timer interrupts. If the process has used its allocated time, then we give the next process a chance. And basically with round robin, what we're considering is that every process should get a share of the processor. And so this differs from a non-preemptive approach because we're trying to ensure that every process has the appropriate ability to share, uh, to make use of the processor. And so with this in consideration, we want to recall our process context block and the appropriate constructs that we have available. And so we can have a control block with the modification to the next PCB, as well as priority. And we can also have a numerator for the state type. And so with round robin, we want to consider it's a preemptive scheduler, and it does require a timer interrupt. So when a process starts, it's going to be given a time slice, and that time slice will limit the continuous CPU time that it can use. So when a process gets dispatched, the timer is set to interrupt at the end of the time slice that has been assigned to that process. And so if a process run for its full time quantum, then the process gets interrupted. The schedule is called to put the process at the end of the ready list, and the process time quantum is reset. And this means that if we have an order of P1, P2, and P3, and each is giving a time slice of 5, then P1 is placed. Once 5 is completed for P1, it will be placed at the end of the process queue for execution. And so if an interrupt occurs, the process current time quantum is reduced by the amount of its time quantum it has used prior to that interrupt. And so in this regards, when we consider each process, we'll assign an appropriate time quantum uh, based on the round robin scheduler to each process. And that is how each process is then assigned to the processor. And so let's take into consideration some wait times for each of the processes. For here we have P1, P2, and P3 with appropriate CPU and IO times that are available. And so let's illustrate the solution that would be needed for a round robin approach for each of the processes. So in this case, we have P1, P2, and P3 with regards to CPU and IO schedules. And using a round robin scheduler, we're going to give each process a time slice of 2. And so we have T1, the time for T1 to be 12. For T2, we'll have 16. And for T3, we'll have 10. And so with this in the consideration, we can calculate W for each of the processes to be 4, 9, and 4. So taking this into consideration, we want to keep in mind that we have various components that are needed in hardware to implement the round robin scheduling algorithm. And so of course we'll have a timer that is utilized um, to provide for an interrupt to the process when each time quantum is is complete. And then we'll need for the interrupt handler to be able to work with the timer interrupt to provide a mechanism for control for the round robin scheduler. And so with each component, we have various layers that need to be um, utilized within hardware. And when we have a program that is running on the processor, once we encounter an interrupt, the timer interrupt will need to take control of the processor. The handler can then save the current state of the process and program and allow for the PCB to be updated and handed to the scheduler. Once the handoff occurs, then we're able to allow for the scheduler to run its algorithm so that it can decide what process should be executed next and dispatched on the processor. And so this can provide for requires a number of system calls that can be executed at a low level that can populate up to upper levels for user interaction and program execution. And so the round robin approach to scheduling needs to make use of an appropriate dispatcher, IO request trap handler, um, a timer interrupt handler, a process termination trap handler, and a IO completion interrupt handler. So there are different considerations that need to be taken into account when working with the round robin approach to scheduling processes. And so when you consider the breakdown of tasks in the OS when it comes to scheduling, you'll have the scheduler that is used. It'll run the scheduling algorithm. It'll get ahead of the ready queue, and it'll set appropriate timer considerations. It'll save the context in the PCB, and it'll restore the context from PCB at the head of the ready list. The timer interrupt handler will mark the PCB as the timer expires. It'll upcall to the scheduler. It'll complete the IO request trap, initiate the IO operation, move the PCB to the IO queue, and mark as awaiting. It'll upcall to the scheduler as well. IO completion interrupt handler will mark the IO buffer completed. It'll move the PCB of the IO completed process to the ready queue, and it'll upcall to the scheduler as well. The process termination trap handler will mark the PCB as halted and freeable. It'll upcall to the scheduler as well. And if we were to consider how these process structures would be represented in the system. We would have the PCB for each process, the kernel stacks that are utilized by the kernel stack pointer, and appropriate user stacks that are utilized with the user stack pointer. And for each process that needs to be executed, these would be taken into consideration. And so this provides a overview of the round robin approach that can be utilized for appropriate scheduling. And so with this in the consideration, we can illustrate the process that occurs for scheduling when denoting what is going to be available for the ready queue. We'll have our IO queue that is also made available. And so with this, we see that P2 is handling an IO complete interrupt for P4's IO. And so this means that the last process to run was P2. So P2's interrupt handler marks P4's IO complete, since that's the IO that was pending on the interrupting device. That means that P4 is back on the ready list, and P2's interrupt handler calls the scheduler. And so P4 is the winner, and P4's return to the ready list that was caused by the IO complete interrupt that P2 took. So this leaves P2 on the ready list and adjusts its quantum to reflect the CPU time it's used. So the processor state in P2's PCB and kernel stack is saved. And then we complete the context switch to P4 by loading state from P4's PCB and kernel stack. This results in us return from using the currently loaded state as well. And so this provides a overview of how scheduling would work with regards to the round robin approach to scheduling. You'll want to keep into consideration that the type of scheduler that gets used by the operating system is going to be dependent on the type of environment. A scheduler that is used for a desktop is going to be different than a scheduler that's used for servers or HPC or cloud environments, as well as embedded systems. And so the environment has an effect, as well as the workload characteristics, to determine the type of scheduler that would be used. And so in this case, when we've been able to outline specific properties that denote each scheduler and how each scheduler prioritizes the various processes, as well as the pros and cons that are associated with each of the schedulers.